Introduction to Heat Treatment, Quenching Media, Gary A. Pace, PE, CWI, Katy, Texas. Okay, so when we're talking about the hardening of steels, as I've said multiple times, we're talking about going from body-centered cubic, we heat up the material, and then we go to a face-centered cubic, and this is one of the things that makes iron a super special material and why it's so useful, is this allotropic phase transformation. So then we turn the whole thing into face-centered cubic crystalline structure, and then we quench it. We take it from this face-centered cubic crystalline structure and we cool it. And there's not enough time for all the carbon that's been dissolved into the face-centered cubic to find a happy resting place in a body-centered cubic material or situation. So it ends up kind of skewed and in body-centered tetragonal, also known as martensite. So this is the basic system. Well, knowing that, we talk about quenching. And when we put it in a graphical form where it's time versus temperature, with temperature on our y-axis and time on our x-axis, you can see that we've got quenching. This is a graphical illustration of what I just talked about. And we're talking about putting a hot piece of metal into a medium. It could be oil, water, some kind of polymer related material that is aqueous based. There's a lot of different options. Salt, quenching. There's a lot of different cooling mediums that we can utilize to get different mechanical properties for our end product, for our steel. So what is quenching? Okay, so quenching is, as I've said previously, it's a critical step in the heat treating process. This is the thing, I guess, that helps make steel what it is. We can take steel from a very high temperature and face-centered cubic, and we slam it into a quenching medium, and it cools down, and it gives us martensite, which is body-centered tetragonal. We're going to use a lot of different, within different industries, there's different quenching media that are used to control the cooling rate. There's water is a favorite. It's the first one we ever used, but there's others that we can use. Oils, different types of salts, all kinds of different things that we can use to manipulate the microstructure to get the mechanical properties that we're looking for in that material. Cooling rate. So things that are some factors that are gonna affect the cooling rate are size of the part. Are we cooling something down the size of a shoebox, or are we trying to cool something down the size of a pickup truck? Depending on what the size of the part is, we're gonna have to, adjust our cooling rate due to the size of the part. Configuration of the part. A lot of the parts might be the same size, contain holes, recesses. These are going to cool more rapidly than if we just had a solid object, depending on the configuration. Maybe there's holes and divots and recesses and different adjustments that are going to be made because of the configuration and the shape of the part. Composition of the part. What is the metal? What is the chemical composition of the material that we are cooling? Used to work for a foundry out on the West Coast, and when the metallurgists and the heat treat people would talk about cooling rates for different materials, the chemical composition came into play. The initial temperature of the part. Different steels and alloys require a wide range of temperatures for heat treatment. What do we need to do? What are we trying to get accomplished? What is our mechanical and mechanical properties that we're looking for the end product? And it gets back to, what are our final properties desired? Hardness, strength, ductility, toughness. What are we looking for in these parts? So here's a property and average cooling abilities of quenching media. I snagged this one out of a military manual, and you can see that it tells you, the cooling rate compared to water. Caustic soda. Caustic soda, sodium hydroxide, 10% is 2 times the cooling rate compared to water. Brine, 10% at 65 degrees. Well, that seems to be double the cooling rate of water. Well, then you get to prepared oil. These oils, their cooling rate is, less than half the cooling rate of water, just pure water. So you can see here, and then by the time you get down to circulated air and still air, it's not cooling very fast. So this chart is I'm sure there's more charts than this. This is probably the boiled down version that they give the enlisted people in the military. But you can see here that there is, the different cooling rates of the different quenching materials in comparison to water. So different quenching media. So let's talk about water. Water quenching, we're just taking hot metal and we're putting it in water for rapid cooling. This goes back to the old days when people used to make tools and farm implements and other items made out of metal that needed a sharp edge or certain mechanical properties such as strength and the ability to hold a sharp edge. Water provides the highest cooling rates other than the ones I just threw out there, the sodium hydroxide and the brine. You're going to get high hardness and good wear resistance, but there's chances that you're going to get high distortion and increased risk of cracking when using water. So, and water's pretty cheap. Oil. There's all kinds of different mineral oils and vegetables oils that they use for cooling. And as it said on the chart, we're going to have a slower quench rate, a slower cooling rate if we use oils as opposed to water. Oil provides a moderate cooling rate, and it's going to give you a good balance between hardness and toughness. And it's going to help reduce the risk of cracking due to the speed that this takes place. So water quenching is going to give us a bigger chance of cracking happening. And this stuff is also going to result in lower hardness. So obviously, if we're using some kind of oil quenching, we're probably not looking for a super hard material. We're going to want hardness, but we're looking to balance that out with toughness and ductility. Polymer quenchants. When we're talking about polymer quenchants, okay, so let's talk about brine. Brine is just water and salt. And there's different formulas that you can use and whatnot, but we're a remedial class in this, so we'll just talk about salt and water. A solution of salt and water for cooling. Well, the thing about this stuff is brine offers a cooling rate that is faster than water, about double. Well, this is going to help your hardness, but there's a whole other list of things you got to think about in regards to uniformity of cooling. With brine, it can be challenging, especially if we've got really complex parts. You can end up with cracking. Some other issues with brine are, what do you do with this stuff when you're done with it? It's kind of a hazard to get rid of because there's so much salt in the water, and it could be an environmental related issue. So there's just some things to think about with brine that you don't have to with just straight water, but something to think about. Brine, quicker and quicker cooling rate, and there's some issues with it. So the effects on heat transfer, the cooling rate during quenching is going to be influenced by the thermal properties of the medium that we're using for quenching. What are we using? Water, oil, brine, caustic soda, air quenching. What do we got going on here? So those are going to have an effect on the heat transfer. High heat capacity and thermal conductivity results in faster cooling rates. Salt water, the brine, has a higher heat capacity and thermal conductivity, so it's going to get rid of the heat quicker, so we're going to have a faster cooling rate. It says here that water has the highest heat capacity, but that's just of the pure substances. Oil and polymer quenchants are going to have lower cooling rates. So, effects on the material properties. The cooling rate directly impacts how much martensite we're going to get, or what the material microstructure is going to look like, and what our mechanical properties are going to look like. Faster cooling rates are going to lead to a harder microstructure. Slower cooling rates with oil is going to give us a tougher microstructure. Not as hard, but it's going to be more ductile and have a higher toughness. And sometimes we're looking for those properties in a material. How we choose these quenching media allows our heat treaters to tailor the materials properties to what we're looking for. So, the different materials that we use in quenching are going to give our heat treaters some different options. Okay, some considerations for quenching. Material type. Different material types require specific quenching media. Depending on what we're doing, what's the material, we may only have limited options. Part size and geometry, this is going to come into play, because if we have issues with it cooling too fast, we could have cracking related issues or any other number of issues that could come into play during the quenching. And distortion risk, distortion and cracking when choosing the quenching media. These are some of the things we need to think about. Questions, comments, thoughts, concerns. Gary A. Pace, PE, CWI, Katy, Texas, TexasWeldingEngineering.com, gpacex@gmail.com.